when it lives on disk. They're trying to, because all the tools that exist so far are focused on taking that static file and reversing it back, all the techniques which have been put in place are trying to disrupt how that file is interpreted, to disrupt those techniques. And it works fairly well. For all the normal tool sets out there, they'll fall over. So we're going to fly through very quickly some of the techniques which are in use. Lots of applications will hide in the packager. So in a PYD type file or pyTeX, pyTapp, they will just assume that because it's wrapped up, people don't understand how to unwrap it, but there will be standard PYCs sitting inside. This is often the technique that's seen used on Windows 32. If this is it, you just, the packages use standard formats, whether it's zip or whatever. It's very easy to get at the PYCs, and then you're home and dry. You can use all the standard toolkits. While I was having a look around for what people were doing, found some source code obfuscation, which is kind of an outlier, and we're not going to discuss it very much after this. But in a similar way to a lot of people when they're distributing JavaScript malware, they will try and confuse the actual, use a lot of exec statements and try and confuse the understanding of the source code itself. There is a product out there that does this for Python. So a quick look, you can see the standard code on the left, and once it's gone through this obfuscation, it pops out different on the right. I haven't spent time trying to undo the differences which it makes. I don't think it will be particularly difficult. I think it would. I've never actually seen it in the wild, so I haven't put in any effort to try and reverse it. However, when I was looking on the vendor's website of this product, I came across another product called PoreSense. It allows you to cat-proof your computer. And it does tell you when cat-like typing has been detected. I assume the guy that writes these has got way too much time. And yours for only $19.99. So I didn't want to put the link in there in case people worried that I was advertising my own cat sense. But if I can give people the link afterwards if they have cat computer problems. So the more interesting side of the anti-reversing is when people use a modified runtime. This means that they will take the standard Python runtime, screw about with the C to change actually how that runs. So it's, in some sense, it's not standard Python anymore. But this means that when they package it up, they can distribute this runtime with their application, and then obviously they can change a lot of the rules. And this is what breaks a lot of the reverse engineering tools for Python which are already out there. So using a modified runtime allows you to do things such as change the bytecode magic number. It's really simple. It's used quite a lot. That first magic number in the PYC, like we say, if it doesn't match the version of Python which is being used, everything just falls apart. Python just refuses to look at it. If they're distributing PYCs with a changed magic number, you're trying to use standard Python on it, your standard Python will just balk. It's defined in import.c. In Python, you can see all these different versions that are out. They tend to increment, for every version of Python, they'll increment the magic number by 10. It's essentially an arbitrary magic number. It doesn't have any cool, like, dead beef or anything. It's just a number. Obviously, the very easy way around this is you can just flick the first 4 bytes back to a version of Python which you know that they're running Python 2.54. Change the bytes back to that, and then you're good to go. Very rarely do you see this used by itself. It's just used as an extra barrier. If people fall at this hurdle, then they're pretty lame anyway. But it does stop out of the box most reversing and decompilers. So it's very simple to implement, but very simple to get around as well. Changing in the marshalling formats. As we said in the Python PYC file, there was 8 bytes of header essentially, and then marshaled formats. The marshalling is controlled by marshalling.c in the Python runtime. If you change how those objects are serialized into the PYC, and obviously you need to do the conversant changes of how you're going to serialize them back out, you can make that as complicated, encrypted, or whatever as you like. If people can't understand how to unpack the code object out, then they can't get access to the code object. This is used quite a bit, and obviously it can be arbitrarily complicated. If you want to reverse at the C layer, you should be able to find out what they're doing. But if they change, it's a lot of effort to find out what they're doing. We'll talk about a better technique to actually get how they're remarshalling things. And opcode remapping. one of the more complicated obfuscations, we've talked about that there's the opcode tables, a number which represents an instruction, and obviously that's a standard across Python. Some developers will rewrite these opcodes, so the instruction that used to be number 40 is now number 80, and mess them all up now. Obviously, if you don't have access to the rewritten opcode table, then trying to get back out from that is a problem. And this is one of the techniques which we've got, we can do again at the Python layer without having to go into the C layer and redo all the work every time they change their opcode table. So the general approach of, given all these techniques, what is the general approach that we're going to take to try and break them? Really want to remove the reliance on the disk, the access to the disk of the PYCs on disk, or the PYO. It would be nice to just let the application undo its own protection, because obviously it's got to undo everything it's done to then execute the code in Python space. So let's let the application undo everything it's done and jump in and then start accessing the objects and not worry about the obfuscations which they put into the file layer. Obviously we need to get in process. This is pretty simple to do. And then once we're in process, we can jump around in memory, access all the objects, and be clever and try and reconstruct source code, but not relying on anything from disk. A nice kind of side effect of this is if you're not relying on things on disk, then you can start to access things remotely. There are a lot of cloud environments that use Python as an access language or a container language. And if they allow you to access kind of into the Python main thread, if they allow you to execute Python code, these kind of techniques will allow you to reverse out source code from the objects which you can communicate with. So even though you might not actually have the physical file, you can still reverse out the source code behind those objects, which is obviously very useful. Moving forward will become increasingly useful, and it's an area certainly that's I'm going to put more work into. I think it's probably more interesting in many ways than some of the stuff that the pyREtic toolkit as it sits so far. So, getting in process. If there is an application which is distributed, it's purely PYCs, we want to get inside that main thread, that Python main thread, so we can execute our own Python. How do we get in? And obviously they've obfuscated their runtime, so we need to use their interpreter to execute their bytecode. So we can't pad it with our own stuff on front. So we need to use their interpreter, but the import rules for Python still apply. We've already talked about that there's a timestamp within the Python runtime. If that timestamp doesn't match, then the file name .py for that PYC will be looked at in preference. So if you create a file, if there was foo_module.pyc, which you're wanting to get in process, rename it to foo_module original, take your module, rename it to foo.py. Your foo.py will have a newer timestamp. It will be accessed in preference to their foo.pyc, and then from your foo.module, you can execute arbitrary bytecode. That arbitrary bytecode can then access back into the renamed object that you've made, and you can mirror out the objects from within it, which I think I've got. Oh, no, I took it out. So you can blindly mirror the module that you've replaced. You can introspect into that, grab all its objects, and proxy between them. So as far as the application is concerned, you're just manning the middle in, but now you've got you're in execution. And I haven't seen any commercial application that's tried to stop doing that. They just assume, oh, it's PYC. No one can get in process. I don't know, it's strange. They seem to have put a lot of effort into other areas and missed this glaringly obvious front door. But, I mean, it's good for us. The non-standard marshalling, which we talked about, it can be arbitrarily complex, essentially. And I found it to be a real pain in the ass. I spent a little bit of time looking at it. Initially, in my head, I wanted to take the obfuscated, marshaled code and kind of get it back to a normal PYC, and then I could put that PYC through a normal decompiler. It was just painful, and eventually I was like, well, there's no point. I can let the runtime do whatever it needs to do to unobfuscate, unmarshal, whatever format they're using, and it will be put into memory as an object like any other Python object. I understand now that Python object is going to be standard. I understand how those objects are. I'm going to be able to get a lot more leverage using the Python objects and every time trying to work out what craziness they've done in their marshalling. So essentially I admitted defeat and started going at the problem in a different way. Opcode remapping, however, and obviously we need to remap their new opcode table, is difficult, or was difficult, but it ended up being quite a simple technique. Obviously, if we're wanting to analyze a runtime, if we want to analyze an object at runtime, and we're looking into that co underscore code object, if the opcodes there are just craziness, then all of our standard tools aren't going to be able to understand what that byte stream means. So we need to understand the opcode mappings if we're to understand the logic and the bytecode which is in that string. Obviously, it's this understanding, this requirement of understanding, which is what the remapping is trying to break. So the simple solution to working out, obviously we don't have access to the opcodes.h that they remapped, and obviously everybody takes away the opcodes.py, so they can't just import and look at their table. So the easier way around this is essentially a known plaintext attack against the object. So if we, as we've already said, the Python instructions are pretty simple. It's like 1 byte and maybe then another 2, depending on. So if we take the standard byte stream on the left, which is standard Python bytecode, and if it's been remapped with the values, you can see that 6.4 has been remapped to 4.4, 4.7 to 11, etc., etc., etc. Now, if we carry on doing this, and we can build up a remap table, so essentially we I'll get to the step-by-step. We stream through as much Python source. We've got access to all their obfuscated modules. They distribute a runtime that's got all the standard library modules, os.py, all the stuff that comes normally. We also have access to the plaintext because that's standard Python. And so we generate the PYCs using standard Python. We've got access to their PYCs that are using their obfuscated, and then we just map them together and be like, all right, 10's changed to 11, 12's changed to 13, build up the new map. Now we've got our opcode map. Now we've kind of got the oracle, and we can use the CO code objects because we understand what they're representing now. To do this in pyREtic, I came up with, file format is probably a bit of a grand name for it, but a PYB file. This is taking the CO underscore code objects from a variety of different, these modules, the standard library modules, and serializing them, literally just rawly concatenating them into a file in a predictable way. Do this for the standard reference Python, do this for your obfuscated Python, and then collide these two streams to get your opcode remapping. That was much easier than looking at the PYCs themselves, because if there was marshalling or obfuscation in place, that would break that looking at both PYCs. So we've gone to kind of an agnostic format, which is I called a PYB, and this allows you to do the opcode remapping, but without having to rely on the unmarshalling, which you may not understand because it's been done in the C layer. So the step-by-step remapping, the big gotcha that kind of I fell for a few times. You've got to have the exact same version of Python running. So find out the version of Python that you've got in process, so you can pull out sys.version and find out what version, but you've got to have it down to the minor version. So if they're running Python 2.5.4, make sure that your reference Python which you're using is 2.5.4. Otherwise, the bytecode which is produced will shift, and then you won't get the collisions that you need. So find the right Python runtime with the unmodified Python. Just